So in this video, we're going to look at a specific type of optimization question where we have a rectangular inscribed in a fixed circle. So here we have a circle that has a fixed radius of 5. So what that means when I say fixed is the circle doesn't change in size. And a rectangle, I shouldn't say triangle, but a rectangle inscribed means that the four corners, the four vertices of the rectangle are in contact with the circle. And if you look at the simulation, so I'm just dragging the rectangle, and as you can see here, the area is changing. So I set the program so we can calculate the area of the green rectangle, and the goal of this question is to figure out algebraically, how do we figure out the maximum area? So if you look at the numbers, there's 48.9, 49.9, 48, 46, 44. So as you can see, as the height of the triangle gets smaller, the rectangle width gets wider, but as you can see, the area is getting smaller. But if I go in the opposite direction, I'm going to drag it down, what you notice that the area is getting bigger, so it's 44, 45, 46, 47, and we want to find the ideal largest number, 48, 49, 49, 49, and then it seems to go lower afterwards. So it seems like the optimal area based on GeoGebra is going to be around 50 centimeters square. So now we're going to actually figure out or show you how to calculate this using the techniques of calculus. So first things first, before we start the algebra, we need to find some sort of common feature that is constant or somehow connected to the circle and the rectangle. So as you can see here, there's something that doesn't change in regards to one of the dimensions of the rectangle, and which is connected to the circle. So the radius is 5. In other words, if I were to draw a line segment from E to D, as you can see here, what you notice is that the rectangle, so when we change the size of the triangle, what's constant is not the base and the height or the length and width of the rectangle, but the diagonal. See, the diagonal is always, in this case, a diameter of 10, and which is connected directly to the circle. So we're going to use this to our advantage when we sort of develop a function to optimize. Because we are optimizing the area of the rectangle, we know that our function is related to the following. Area is equals to length times width. So in our case, you have a choice what you want to optimize. Do you want to express A in terms of L, meaning we're going to have to develop a function, or A in terms of W? So because we're using L and W, we can actually go to our diagram and label what is length and width. So in our case here, the length is from here to here, so L. So in other words, I'm labeling my diagram, I'm letting L be the length, and I'm going to let from D to F, or the height, be the width. It doesn't really matter what you call length and width. And the next thing is, what else do we know about this diagram? So as you can see here from the previous few seconds ago, we know that the diagonal here is going to be 10, because we know that the radius, which is given to us, is already, the radius was 5. And the next thing we're going to do is the following. So we need to somehow think of another relationship in terms of a shape that is connected to the three measurements. So if you notice L, W, and 10, they form what type of shape? They form a right angle triangle. So what that means is there is some sort of a feature here that I think you've learned in grade 9 or in grade 8 that's connected to the length and the width and the 10. And that is the Pythagorean theorem. So the Pythagorean theorem says a squared plus b squared is equals to c squared. In other words, I'm going to put here on the side, Pythagorean theorem is equal to L squared plus W squared is equals to 10 squared. This is what I call the constraint equation, meaning no matter how you change your rectangle, this relationship will not change, because there's always a right angle triangle inside this rectangle. So now we are ready to actually create our function. So this is where you have a choice. Do you want A of L, or do you want A in terms of W? So what we're going to do right now is you need to make that choice. So I'm going to just say a of w. So I'm going to create a function which is in terms of a of w. Yes, I know that this statement is the area of a rectangle. However, I do not want to express a area in terms of two variables because I already chosen that we have to express in terms of w. So this L has got to be somehow reformatted or replaced. And what are we going to replace this with? Well, we have a constraint equation. In other words, we're going to isolate for L and then substitute it back into the function that we're going to optimize. In other words, let's actually isolate our constraint. So I'm going to get L squared is equals to 100 minus w squared. You take the square root and you get 100 minus w. Just a note, when you do when you take the square root of of both sides, it is not the following. So please don't do this. And if you do that, you'll get this, which is a linear relationship, and which is not the case. All right, so now we have our constraint equation. I'll highlight this in red, and we're going to substitute. Anytime I see a L, I'm just going to replace it with that square root. So in other words, my function right now is going to be, I'm just going to switch it around because I have to have the w first. Anytime I see a L, I replace it with my constraint equation. So 100 minus w. And right here is our function we are going to optimize. So before we do the calculus portion, we need to figure out the endpoints or the restrictions of our variable. The reason why we're figuring out restrictions is because w is not ER, meaning the width cannot be a negative and it cannot be 0. So that means a width has to be a certain value. So to the left, let's look at the simulation. So the width, as we define, is the height, so from D to F or from C to E. So what's the smallest based on the simulation that the height of the width of the rectangle can be? So we know that if the width is 0, when we have no rectangle, as you can see here, so we know that the width has to be greater than 0. But what's the maximum in this case? What's the highest that the width can be? So let's look at the height or the vertical sides. So as you can see here, as you can imagine, the width, the maximum width it can be is pretty much the size of the diameter. In other words, the width over here to the right hand side, based on my diagram, based on the GeoGebra simulation, is going to be between 0 and 10. However, some of you are wondering, well, Miss, I don't have this visual simulation. How can I actually figure out these two numbers algebraically? And I'm going to just show you how right now. So you're going to take your function. Okay, and we know for a fact that the area, a of w, must be greater than 0. You cannot have a negative area. So in other words, you're going to have to solve an inequality. So if you recall back in advanced functions, we solve for inequalities of rationals and polynomials, but the only difference in this case is right now we're going to determine the inequality of a product of a square root and a linear. But fortunately, we have it in factored form. So recall in advanced functions, we need to find the zeros of each piece. So we know that this w gives you 0, and if you set this factor here to 0, you take the square root on both sides, you end up getting this, and w is going to equal to, I believe it's going to be, I think I made a mistake on the right hand side. There should be a square here before, a square here before, and a square here before, square, and a square. All right, so let's actually solve for this, and we end up getting, you bring the w and then you deal with the signs, and we end up getting plus minus 10. But we know that the w cannot be negative. So when we set up our interval chart on the right hand side, right over here, I'm going to put all my factors, w, which is this one here, square root of 100 minus w squared. This pretty much gives me the area. And we know our restrictions based on this, it's got to start from 0 and it goes to 10. I'm not going to include the negatives. And so I'm going to just cross this out because we know that the width cannot be a negative. And we know that the width here is, so this is gone. So now we're just going to test the factors. So all we have to do is test a number between 0 to 10, such as, for example, 1. So if I put 1 in here, I get a positive, positive, positive. So that means this zone is good. But what happens if I go above 10, such as like 11, all right? So, or 20. Well, W is 20, it's positive. But if you put 20 in here, what's going to happen? it's not going to work. You're going to get a not available because you cannot take a square root of a negative number. In other words, not available. So in other words, this is our restriction. So now that we have our function to be optimized and we now have our restrictions, what I did was on Desmos, I actually typed in the function so we can see visually what the function looks like. So over here, up here, it was w and 100 minus w squared. I'll just use x in this case. And let's have a look at our graph. So let me just describe what this means. The x-axis is your width, and the y-axis is actually your area. In other words, if I were to write this out, this is your area, and this is your width. And based on this picture, where is the maximum optimal point? And now keep in mind, if this has to be scratched out because this is not part of the restrictions, so it is in this upper area, which is the restriction. So in other words, over here where the arrow is, I'll use my arrow here, this is what we want. This is our answer here based on our function and the restriction. So we're going to have to solve this using calculus. And how are we going to do that? Well, let's figure out the first derivative and figure out where it's 0, and then we're going to have to do all the checking to verifying whether it's a max or min. So in the first step, I just copied down the question, and because we're going to have to take the derivative, we're going to have to review or go back to all the derivative rules. So here is a product of two functions. In other words, I'm just going to change the radical into a power exponent form. We will be using product rule and a combination of power and chain rule. So in this case, I'll be using the product. So we end up getting this. So I'm not going to go through all the intricate details of how to get this using the chain, product, and power rule. So we end up getting this. But however, we need to solve for where the slope is 0, or where the critical points, in other words. So everything goes back to curve sketching to look for critical points. So in other words, we're going to have to clean this up. So this is one of the functions where it's more difficult than a rational or a polynomial. So that's why I'm actually explaining this particular example, unlike the other ones. So over here, we're going to have to clean this up. But if you notice in these two groups here, they have something in common. They have this factor in common. And recall that when you want to factor something out, you always factor the one with the least exponent value. In other words, negative 1 over 2. So let's actually factor it out. So I'm just going to show you the micro steps. I'm just going to take this and divide everything. So I'm just showing you all the steps. Divide each piece or each section by half. So in other words, I am going to get the following. So notice here that the bases are the same. So it's still 100 minus w squared, but all we have to do is subtract the exponents when you divide same bases. 1/2 minus minus 1/2 becomes positive 1. This one here, I'm not going to put that down. Now over here, what happens? We end up getting, it's gone. So but here, this is reduced, and we end up getting 1/2 times negative 2w, which I will clean up. And because I'm factoring out something, I'm just going to put it outside here. So 100 minus w squared to the power of negative 1 over 2. So once we're done, we're going to clean up the inside. For me, I'm just going to introduce back the denominator. So this part here, I'm going to put it in the denominator, 100 minus w squared, 1/2. And then over here, the numerator to the power of 1, nothing happens to the bracket, 100 minus w squared. And then here, you're going to end up getting negative w squared when you multiply these two things. And we end up getting 100 minus 2w squared over 100 minus w squared, 1/2. And this is where we do exactly the same thing as curve sketching. We want to figure out where things are undefined and where the slope is 0. So in other words, we're going to set a of w to equal to 0, a of w to not defined, and then we set the numerator to equal to 0. We work things out. We end up getting this at the end, and we end up getting positive root 50. But of course, we're only going to take the positive root 50 because we had restrictions up here indicating that our width has to be greater than 0. This one here, we do the exact same thing. W squared, 1/2. We set it to 0. We want to figure things undefined. We square everything both sides. We end up getting the following. And then we bring the 100 over, clean things up, and we end up getting positive negative 10, but we know that the width is going to be 10 positive. So the next thing you're going to do is, if you didn't have the Desmos to show you the max and min, you're going to have to do everything algebraically. We have to classify whether this is a max or min, but of course we need to figure out if there is a a y value or an a value. So in other words, if you take the function here, if you take a and sub into root 50 into the original function, what do you get? Same thing for here. If you sub in 10 into the original function over here, what do you get? So I'm just subbing this in. So the one to the right, undefined, where w is 10, if you sub 10 into here, you're going to get 0. The area is 0. Over here, when we substitute root 50, I'm just going to sub it into here, root 50 times this. We end up getting the following. I'm just going to show you all my steps, and we get 50. Okay, so we do have a output. We do have a dependent variable. And the second last thing you're going to have to do, or the third last thing, you're going to have to verify whether it's a max or min. In other words, we're going to have to do the interval chart. So in other words, I'm just going to take a black pen, just set things up, okay? So now we're going to have to verify. So we're going to have to check this one here. So this is our critical point, so root 50, okay? And then keep in mind we have our restrictions. So I'm going to put 0 here. I'm going to just remove that. And our maximum was 10, all right? And over here, I'm going to take this out. And then we just have to check whether it's a max or min by subbing into the A prime. So A prime W. And recap, A prime W looks like this over here. In other words, I'm just going to sort of copy the steps. I'm going to do everything. I'm showing you all the steps. So numerator is 100 minus 2w squared. Denominator is square root of 100 minus w squared. And what happens? Well, we know that this piece here will give you 0 because that's how we found out this number here from the numerator. Now, what happens if you sub in, for example, give me a number that's to the left of root 50, such as w is equals to 1. If you sub 1 into this piece here, you're going to get a positive and a positive and a positive. That's great. That means the graph is going up to the left, to the left of this point here. Now, this give me a number to the right of root 50. Root 50 is around like 8. Let's just say 9. Let's just say w is 9. When you sub in 9 in here, 9, 9, 8, you're going to get a negative, and then here you're going to get a positive. I can tell you can get a positive because square root of something is positive, and you get a negative. So right now, based on our first derivative test, we can say therefore that when root 50 is a max. And the very last thing we're going to have to do is check the endpoints, or the end behaviors. In other words, we have a root 50, which we got was 50. So this is our centimeters squared. We'll just assume it's centimeters. We did actually talked about a of 0, which so happens to be, remember our restrictions was between 0 and 10. So over here, we subbed in 10 down here, and we got 0. That's great. So we know that this seems to be like the biggest number so far compared to 0. And then the last thing is, well, if you sub in w for 0, well, over here, well, we know that when the width is 0, you're not going to get an area. And therefore, we can say that root 50 is the ideal, optimal dimension for your rectangle. And in this case, you get the area is going to be root is 50 centimeters square. So the shape, if I were to, the question was just asking for the optimal area, but if I were to just change the question and say, what kind of shape will you get? Well, if we found the width, we can actually find the length. So how do we find the length? Well, we know that based on the constraint, remember that triangle Pythagorean equation that we got? It was L squared plus W squared is equals to 100, I believe. Yes, 10 squared. And we actually isolated for this number here, which was 100 minus W squared. So all we have to do is find the length. We already know that the optimal dimension for the width is root 50. We just sub this in, and let's actually solve for the length. We end up getting root 50 squared, and you end up getting, at the end, I'm not going to go do all the details, we end up getting root 50. In other words, the length and the width are the same, and what kind of shape is that? Oh, it's a square. So the optimal size for the rectangle, well, a square is a type of rectangle, it's just all the four sides are the same, is a square. Just one more additional note, and this is more regarding to communication. So if I look at this one here, the red parts here, technically speaking, I should not be writing this in function notation because technically speaking, 0 is not part of the function. So there, in terms of this, what this means is, that means W is part of 0. I mean, 0 is part of W. So in other words, this is not really an ideal notation. We should have been using a limit notation. What that means is the limit as W approaches 0 of the area. And in this case, we're approaching from the right-hand side because we can't approach from the negative width, all right? And then we just sub it in and then we get there. So the technical part is, yes, we are subbing the 0 into here, but in terms of format-wise, this would be not the ideal format. Same thing for this part here. You would have to do the width. What happens to the area when the width is 10? Now, width is 10 is coming from the left because our restrictions, there's nothing to the right of 10, so we're going to come from the left of 10. In other words, the technical thing is still the same. You still take 10 and sub it into the function here, and you end up getting 0. So this technically, communication-wise, should be the more proper way.